Hi guys, welcome to lecture number 17. In the previous lecture we have covered the DC transient, okay, and in this lecture we will be starting the AC transient free condition. See, if we apply DC voltage V to any RL, RC or RLC network, let us take one example like RL network, okay. If we apply the DC source with RL network, and if I will close this switch at t is equal to any time, let us say at t is equal to 0, then you will get response of the circuit it is equal to transient state plus steady state, okay. Now for DC circuit it is not possible that we can make transient free circuit, okay. However, in AC circuit, if we apply AC sources here like V is equal to Vm sine omega t, then there may be the possibility that for any time t naught this transient state will die out, means the response will be only containing a steady state. So we will see these things in today's lecture. First we will see for RL circuit. Let us take RL circuit first, in which we are applying the AC voltage Vt is equal to Vm sin omega t plus phi, and we are closing the switch at t is equal to 0. Then what I said it to you, that the complete response of the circuit will be, mathematically we can define like complementary function plus particular integral. However, it can also be defined like natural response plus forced response, or transient response plus steady state response, or up to 5 time constant or greater than 5 time constant. So finally the response of the circuit you will get, this is the transient state which will be the exponentially decaying function, and this is the steady state response, okay. Now in order to find the steady state response there are two methods. First one is the phasor approach method, and second is the Laplace transform approach. You can go by any one of the method, no problem, but since I have covered the Laplace transform approach method, so I will go with Laplace transform approach. I will explain to you the phasor approach later on, okay. So first find the steady state response of this circuit. So I have already explained in lecture number 11 how to find the steady state response. So if you guys are having any problem while finding a steady state response by Laplace transform approach, then see the first 10 minutes of lecture number 11, then come to this lecture, because I will write the equation, a steady state equation directly. Let us take, this is my input voltage Vm sin omega t plus phi, and I have replaced this whole circuit by one block having transfer function I of s upon Laplace transform of I of s upon source V of s, okay. These all things I have explained you in lecture number 11. Go through that lecture, you will understand better. Now I have replaced the circuit by one block having transfer function 1 upon r plus ls. How I am getting this? See, what is transfer function? Transfer function is the I of s upon V of s, that is equal to y of s, and that is equal to 1 upon z of s. Now z of s is nothing but r plus ls, that is equal to 1 upon r plus ls. These all things I have explained in lecture number 11, so go through that. Now if I am applying the input Vm sin omega t plus phi to any LTI system, then the response, that is the steady state current, I will get Vm a naught sin omega t plus phi naught, where a naught can be found by a magnitude of h of j omega at omega is equal to infinite frequency, and phi naught can be found by angle of h of j omega at omega is equal to input frequency. Now magnitude of h of j omega will be, let us find first, h of j omega is equal to, put s is equal to j omega, you will get r plus j omega l. Hence magnitude of h of j omega will be 1 by under root r plus omega square l square, and angle of h of j omega will be minus tan inverse omega L upon R. Now the complete response of the circuit, that is the RL circuit, is given by IT is equal to k e to the power minus t upon tau. This is the transient state which is decaying exponentially, and a steady state response is given by Vm A naught. A naught is this upon under root R square plus omega square L square sin omega t plus phi plus, no, this is not plus, this will be minus tan inverse omega L upon R. So this is the complete response. Now I have to make this response transient free, means anyhow I have to make this 0, means we have to make this the value of k is equal to 0. Now tell me, at t is equal to 0, the current flowing in this circuit at t is equal to 0, if I am closing this switch, then inductor will behave like an open circuit, so I of 0 will be 0, means at t is equal to 0 this current will be 0. Okay, so put t is equal to 0 here, you will get k e to the power 0 is 1 plus Vm upon under root R square plus omega L square sin omega t, that is 0, t is equal to 0 means 0, plus phi minus tan inverse omega L upon R. Hence we can say that k is equal to minus Vm upon, I am writing this as a z, no problem, sin phi minus tan inverse omega L upon R. Okay, if I will make k is equal to 0, then this response, the response of the circuit will be transient free. Got it? So in order to make k is equal to 0, what I have to do? I have to make this sinusoidal term is equal to 0, means sin phi minus tan inverse omega L upon R is equal to 0, means phi minus tan inverse omega L upon R is equal to 0. Hence phi is equal to tan inverse omega L upon R. What does this mean? This means if I will make the initial phase of the input voltage phi is equal to tan inverse omega L upon R, then I will get the response of the circuit IT transient free, means I will not get this k e to the power minus t upon tau term. Got it? So in this way we can make any kind of RL circuit transient free by making initial phase phi is equal to tan inverse omega L upon R. Now suppose this switch is closed at t is equal to t naught. Okay, so if this switch is closed at t is equal to t naught, then you will get the transient free condition omega t naught plus phi is equal to tan inverse omega L upon R. This is the condition for making RL circuit transient free. This is when the input, the supply input voltage is Vm sin omega t plus phi. What will happen if the input voltage is Vm cos omega t plus phi? Same procedure can be applied and you will get IT is equal to k e to the power minus t upon tau plus steady state response, you will get same, that is equal to Vm by Z in cos form, not in sin form, omega t plus phi minus tan inverse omega L upon R. Same procedure you will apply which I have already explained in lecture number 11. Now in order to make this response transient free, what we have to do? We have to make this cosine term is equal to 0. So overall cos of omega t plus phi minus tan inverse omega L upon R is equal to 0. Like we have explained here how we are making k is equal to 0. Same approach can be applied here. So in order, this can be done when omega t plus phi minus tan inverse omega L upon R cos is 0 when at equal to pi by 2. So finally I will get omega t plus phi is equal to pi by 2 plus tan inverse omega L upon R. This is the condition when you apply the cosinusoidal voltage. Then the condition for making the circuit transient free will be omega t plus phi at t is equal to t naught, where t naught is the closing time, plus phi is the initial phase, is equal to pi by 2 plus tan inverse omega L upon R. So finally what is the conclusion? The conclusion in RL circuit is, if excitation is sinusoidal, then the network will be transient free when the omega t plus phi at t is equal to t naught. This is the time when circuit gets closed, is equal to tan inverse omega L upon R. And if excitation is cosine, then network will be transient free when omega t plus phi at t is equal to t naught is equal to tan inverse omega L upon R plus pi by 2. These two formula you have to keep in mind, because the question is asked directly that find the time t naught at which the circuit will be transient free. So you have to just see the excitation whether it is sinusoidal or cosinusoidal, and you have to put the formula. Okay, we will solve some problem based on this. Before that, let us take RC circuit. Same procedure can be applied. We can replace this RC circuit by one block having transfer function that is equal to V naught of S upon Vi of S. Okay, so first find the transfer function of this block. Transfer function is equal to V naught of S upon Vi of S, that is equal to 1 upon Cs R plus 1 upon Cs. So this will be 1 by 1 plus RCS. Now we replace the whole circuit by one block having transfer function 1 by 1 plus RCS, and we will find the response VCT, that is given by steady state, that is equal to VC steady state response. Okay, what we did, we replaced the whole circuit by one transfer function, and in order to find the steady state response, that is given by Vm A naught sin omega t plus phi naught, where A naught can be found by magnitude of h of j omega, where and phi naught can be found by angle of h of j omega. Okay, now magnitude of h of j omega will be 1 by under root 1 plus RC whole square, and angle of h of j omega will be minus tan inverse omega RC. This we have explained in lecture number 11, how to find the steady state response of RC circuit. So the complete response is given by Vc of t is equal to k e to the power minus t plus, this will be omega RC not RC. Okay, so Vm upon 1 by 1 plus omega square R square C square sin omega t plus phi minus tan inverse omega RC. So at t is equal to 0, if I am closing the switch at t is equal to 0, then I am considering that the voltage across capacitor is 0. So at t is equal to 0, Vc of t will be 0, means if I will put Vc of t will be is equal to 0, then I will get k plus something. So finally I will get k is equal to minus Vm upon this under root 1 plus omega square R square C square sin omega t plus phi minus tan inverse omega RC. So in order to make the circuit transient free, we have to make k is equal to 0. So how will I make k is equal to 0? By making this sinusoidal term is equal to 0. So if you will make sinusoidal term is equal to 0, then you will get omega t. At t is equal to 0, this will be 0. Okay, so phi minus tan inverse omega rc is equal to 0. So phi is equal to tan inverse omega rc. This will be the condition when you close the switch at t is equal to 0. Suppose you close the switch at t is equal to t naught, then the response of the circuit will be transient free when omega t plus phi at t is equal to t naught will be tan inverse omega rc. Got it? Only I have to make the value of k is equal to 0 in order to make the transient free circuit. Okay, so this is the condition for making transient free RC circuit. Got it? This you will get when you will supply the input, that is equal to Vm sin omega t plus phi. What will happen if I will apply the input voltage in cosine? Means if I will apply Vm cos omega t plus phi, if I will apply Vt is equal to Vm cos omega t plus phi, then you can find the steady state response that will also be in cos term. So finally you will get k is equal to minus Vm upon under root 1 plus omega square r square c square cos of phi minus tan inverse omega rc. Same procedure by using same step. Now you have to find and you have to make the k is equal to 0. So in order to make the k is equal to 0, you have to make this cosine term is equal to 0. So finally you will get phi minus tan inverse omega rc is equal to cos will be 0 at pi by 2. So phi is equal to tan inverse omega rc plus pi by 2. This is the condition when you give the supply Vm cos omega t plus phi. If you are closing the switch at t is equal to t naught, then you will get omega t plus phi at t is equal to t naught will be tan inverse omega rc plus pi by 2. So in a nutshell, we can conclude that if excitation is sinusoidal, then the network will be transient free when omega t plus phi at t is equal to t naught is equal to tan inverse omega rc. Or if the excitation is cosine, then the network will be transient free when omega t plus phi is equal to tan inverse omega rc plus pi by 2. So you have to remember these four formula in order to solve the questions in AC, RL and RC circuit. Okay. Now let us see what will happen in RLC network. So if you will apply AC voltage Vm sin omega t in any RLC network, then the characteristics equation of RLC network will be R plus Ls, this XL is equal to omega L replace omega by S, then you will get Ls plus 1 upon Cs, that is equal to 0. Characteristics equation is given by this. So S square plus R upon Ls plus 1 upon Lc is equal to 0. This is the second order differential equation you are getting. So the solution will be e to the power minus alpha t k1 sin beta t plus k2 cos beta t, where alpha and beta are the roots of this characteristics equation. Got it? So at for any time t is equal to t naught, you will not get transient free circuit. If we evaluate k1 k2 with initial condition, then one will be the function of sine and other will be the function of cos. So no time will satisfy both sine and cos equal to 0 simultaneously. So transient free condition is not possible in RLC circuit. Now conclude whatever we have studied today. If the excitation is sinusoidal and the circuit is RL, then transient free condition will be calculated by using this formula. If the circuit is RC, then by using this formula, and if the cosine excitation is given, then the transient free condition can be found by using this formula for RL circuit and using this formula for RC circuit. Let us solve some problem. This has been asked in GATE exam. Input is given as sin omega t and there is RL circuit is given and we have to find the value of t naught. This is switch is closed at t is equal to t naught. We have to find the value of t naught for transient free condition. Now tell me, excitation is sinusoidal, okay, and circuit is RL and switch is closed at t is equal to t naught. Then which formula we are going to apply? We will apply this formula for RL circuit and the excitation is sinusoidal. So what I will do, omega t naught plus phi, that is equal to tan inverse omega L upon R. Now phi is equal to what? 0, because sin omega t it is not phase shifted. So phi is equal to 0. I can write omega t naught is equal to tan inverse omega L upon R. Okay, omega is equal to 2 pi f. Okay, so finally I will get t naught is equal to tan inverse omega L upon R upon 2 pi f. Put the value of f is equal to 50 hertz. Okay, the value of L is given by 0.01 Henry and R is equal to 5 ohm. You will get t naught is equal to 1.78 millisecond. Means if we will close this is the sine wave, okay, 1.78 millisecond some will lie somewhere here. Means if you close the switch at t is equal to this one 1.78 millisecond, then you will not get transient response in this circuit. Got it? Now see the second question. What the second question is saying? Second question is saying also find t naught for cos omega t. Means if we give the input cosine wave cos omega t in RL circuit, then which formula we have to apply for transient free condition? That is equal to this formula omega t plus phi at t is equal to t naught is equal to pi by 2 plus tan inverse omega L upon R. So omega t naught plus phi, where phi here phi is 0 because we are not shifting the input phase. Omega t naught is equal to tan inverse omega L upon R plus pi by 2. Now find t naught. You know omega L R, so you can easily find t naught, and t naught is you will get 6.78 millisecond. Now see the third question. Third question is saying if input voltage is equal to cos omega t minus phi, means input voltage is cos omega t minus 10 degree, then find t naught. So excitation is cosine, okay, and having initial phase phi is equal to 10 degree. So we can write the formula omega t naught plus phi is equal to tan inverse omega L upon R plus pi by 2. Okay, now we have to put the value of phi in radian. Here it is given in 10 degree. So phi in radian is calculated by pi by 180 into that is the degree. So you will get pi by 18. Okay, put the value of omega phi in this equation, the value of L and R, you will get t naught is equal to 7.3 millisecond. So in this way we can make any type of AC circuit transient free by switching at a different time depending upon the value of inductance and resistance and the initial phase in the input excitation. Let us solve one more problem of RC circuit. Now the RC circuit is given and we have to find T naught for transient free network. See, first input is cosine and the network is RC. Now see the formula. Input is cosine and the network is RC. Means we have to apply this formula omega t plus phi is equal to pi by 2 plus tan inverse omega RC in order to make the circuit transient free. So omega t naught plus phi is equal to pi by 2 plus tan inverse omega RC. Okay, now phi is the this one pi by 4, so omega T naught plus pi by 4 is equal to pi by 2 plus tan inverse omega RC. Now you know the omega. How much is the omega? Omega is equal to 2. So put the value of omega, put the value of R, put the value of C, you will get T naught is equal to 0.785 second. Means if I will close the switch at t is equal to 0.785 second, then I will not get transient response in this circuit. Now the second question is saying if input voltage is sin 2t plus 5 by 4, then find T naught. What is the excitation? Excitation is sinusoidal, and we have to find the T naught in RC circuit. See the formula. Excitation is sinusoidal and the circuit is RC, so we have to apply this formula. Omega t plus phi is equal to tan inverse omega RC. So apply this omega t plus phi. So finally T naught you will get 0 second. Means if you close the switch at t is equal to 0, then you will make this circuit transient free. So that's all about this lecture. In the next lecture we will start two-port network and we will see some problem based on two-port network. If you guys understood the concept, then please like this video and subscribe to this channel. For doubt solving you can join our Facebook group. Thanks for watching this video.